Swayam Prabha. Digital India. Educated India.
So, today we are going to begin the final tutorials of this series, that is on the chemical reactions. So, we will take up some problems related to the adiabatic flame temperature calculations and during the combustion process, and what about the exergy destruction during different processes that takes place through these tutorials. So, first we will begin with this problem. Here hydrogen is burnt completely with the stoichiometric amount of air during a steady flow combustion process. Now, it is given that both the reactants and the products are maintained at 25 degree centigrade and 1 atmospheric pressure. So, what is happening? We are having a reactor. Okay. So, in this reactor, hydrogen is entering at 25 degree centigrade, and also stoichiometric amount of air is supplied. So, that is air, and that is also at 25 degree centigrade. Okay. And here it is a steady flow combustion process, and the products come out of this reactor at 25 degree centigrade. Okay. And in this process there is some heat transfer to the surroundings. Okay. So, let us say Q is the amount of heat that is transferred during this process. So, first we can start with the stoichiometric balance equation. So, we have hydrogen plus air. So, in air you have 1 mole of oxygen and 79 by 21. So, 79% nitrogen and 21% oxygen, right. So, for each mole of oxygen you have about 79 by 21 moles of nitrogen, that is 3.76, right. The ratio, the 79 by 21 is 3.76. So, let us say 3.76 times N2, and that gives you the products, that is water, and you will have nitrogen, because nitrogen, we will assume that nitrogen remains as an inert gas and it does not react with the other reactants, and but at high temperature it may be possible to dissociate nitrogen into nitrogen atoms, and then it can react with oxygen to form nitrogen oxides. But we are assuming that it is a complete combustion, and then the nitrogen is an inert species which does not participate in the reactions. So, if you see, if I write the balance equation, it will be, here you will have 3.76, right. Now, to balance this you have to multiply, let us say you have to come up with some theoretical, A theoretical. So, A theoretical has to be determined. Okay. So, if you write it, then let us say here you will also have nitrogen, which is 3.76 times A theoretical. Okay. Now, it is easy to figure out what is the value of A theoretical, but for this we need to do the atom balance. So, you see that if you make it hydrogen atom balance, in this side, left hand side you have 2 and the right hand side also you have 2. Okay. Now, if you balance oxygen in the oxygen atoms, in the left hand side you have 2 times A theoretical, whereas on the right hand side you have only 1, right, only 1 atom of oxygen. So, that basically will give you that A theoretical, which is half. Okay. So, now if I write down this equation after substituting this value, I will get it as H2 plus half oxygen plus 3.76 nitrogen, that is going to H2O plus 1.88 times nitrogen. Okay. So, this is the actual balance reaction for the stoichiometric amount of air reacting with hydrogen. Now, it is interesting to see that both the reactants and the products are at the same temperature, right. So, what is happening? There is a chemical reaction that is taking place inside the reactor, and obviously there will be a rise in temperature within the reactor, but then you are transferring heat to the surrounding, to the you are transferring heat to some process, and therefore, you are reducing the temperature of the product gases to 25 degree centigrade. Okay. So, we have to determine what is that Q out of this reactor. So, for this we will again look into that first law of thermodynamics, that basically says that E in minus E out, that should be equal to delta E system. Now, since it is a steady flow combustion process, so that this should be equal to 0. So, that means, and also there is no work done, right. So, work done is also 0. Okay. So, we can basically write this, and finally, we will get whatever Q out, that should be equal to sum of all the species mole fractions times enthalpy. Okay. So, P stands for the product, right, and here it is the enthalpy. So, I am writing first the enthalpy of formation of each species, and then I will write the sensible enthalpy part, right. So, this is the sensible enthalpy part, which is basically the enthalpy. This enthalpy H is basically, it can be obtained at a particular temperature, whereas H naught is basically enthalpy at 298 Kelvin, right. And you all know that the bar above enthalpy is basically says that this is the molar unit, right. Bar represents molar unit, right. So, enthalpy will be kilojoule per kilomole kind of. Okay. But if I remove this bar, and if I, so basically H bar means that it is molar enthalpy, that is kilojoule per kilomole. Now, if I write H only without any bar, then it is basically the mass based enthalpy, right. The unit will be kilojoule per kg. Okay. So, we are here writing because we are now making the balance of the energy, and here we know the moles of each reactants species and the number of moles of the product species. We are taking the molar form of the enthalpy. Okay. So, first part is basically the enthalpy of formation, and this part is nothing but the sensible enthalpy, right. I believe you all have studied this during the course of thermodynamics. Okay. So, this is the sensible enthalpy, which is nothing but the difference between the enthalpy between two temperatures, right. So, H naught is the reference temperature, right. So, 298 is basically the reference temperature, and H naught denotes the enthalpy at the reference temperature, whereas this H bar represents enthalpy at any other temperature T. Okay. And the difference between these two is the sensible enthalpy. Okay. So, now to continue it further, so this is so from this first law of thermodynamics, when you study when you plug in all these energy interactions, you will get minus Q out equal to the sum of product of the species mole fractions times the enthalpy of the product, and then you have to subtract this for the reactants. Okay. So, R stands for the reactants. Okay. And again I will write the same thing, enthalpy of formation plus sensible enthalpy. Okay. So, this is the form that is quite useful, and we will be using this relationship more or less throughout this tutorial. Okay. So, how you are getting this? You are getting it from the first law of thermodynamics after considering all the energy interactions. So, what are the different energy interactions? There will be energy interactions due to the flow. So, the reactants are coming in. Okay. So, all these reactants have some specific enthalpy, some enthalpy. So, you have to consider all the enthalpies that is coming in due to the reactants, and some of this and the product species are going out of the system, and you have to consider all the energy interactions due to the products leaving the reactor, and also there is a heat transfer to the surrounding, that is basically Q out, okay, but there is no work done, right. So, W is basically 0. So, there is no work interactions, but there is a heat interactions. So, if you consider all of them, so basically E in minus E out is equal to 0, and you now put all these energy interactions, you will get this relationship. Okay. So, now what I have to do? I have to plug in different numbers, okay. What are the enthalpy of formation of different product species, and what are the what is the sensible enthalpy. Similarly, for the reactants, what are the enthalpy of formation of the different species that is coming in, and what are the sensible enthalpy, right. Then that we have to calculate. So, now what I will make is a table, and in this table I will summarize different species. So, let me write it as substance, or basically species. I could have written species, and here I will write enthalpy of formation in kilojoule per kilomole. So, what are the different species available in our system? H2, O2, N2, and H2O is the product, and it is coming out as liquid, okay, because it is written that the water water in the product exists in the liquid form, okay. So, all the water has condensed and it is in liquid form. So, now we have to write all the enthalpy of formation. Since these are basically the pure species, enthalpy of formation of pure species is basically 0, okay, whereas H2O the enthalpy of formation, if you look at the table, you will find it as 285,830, that is kilojoule per kilomole. So, please take the enthalpy of formation of liquid water, okay. Sometimes it is available for the vapor phase, but here all the water exists in the form of liquid. So, you have to take enthalpy of formation for the liquid water, okay, which is this value, okay. So, if you can plug in these numbers in the relationship that I just wrote, now interestingly you see that the sensible enthalpy is basically 0 for both the product species and the reactant species, because the reactants are also entering at 25 degree centigrade, which is the reference temperature 298 Kelvin. So, sensible enthalpy is basically the difference between these two terms, right. So, this is basically 0 for all the species. Similarly, the product species are also coming out at 25 degree centigrade, which is the reference temperature. Then again this is equal to 0. Now, you are basically left with all the enthalpy of formation of the different species. Now, again if you look at for the reactant species, which are H2, O2 and N2, these are the pure species, and the enthalpy of formation for this species are basically 0, okay, as I have written in the in here, okay. So, enthalpy of formation is basically 0. So, I can substitute this enthalpy of formation, that is 0 here, okay. So, what I will be left with this minus Q out equal to summation of Np times Hf naught. Now, again what are the product species? Product species are H2O, and H2O is in the liquid form, okay. H2O is in the liquid form, and you have nitrogen. Again the enthalpy of formation of nitrogen is basically 0, and sensible enthalpy is 0 because nitrogen is coming at 25 degree centigrade. So, I can write minus Q out, that should be equal to, now on the product side you have 1 mole of water times enthalpy of formation of water, right. So, I am writing 1 times minus 285,830, okay. So, that is it, right. There is nitrogen, but enthalpy of formation of nitrogen is 0, okay. So, I hope it is clear. See the reactants, the enthalpy of formation of all the reactant species, that is H2, O2 and N2 are 0 enthalpy of formation. Similarly, sensible enthalpy part is also 0. So, basically the enthalpy of the reactant stream is 0, right. Now, if you look at the product stream, enthalpy of formation of liquid water has to be considered, enthalpy of formation of nitrogen is 0, and both the sensible enthalpy of water and the nitrogen is 0 because they are coming out at reference temperature 25 degree centigrade. Okay. So, we have to only consider enthalpy of formation of nitrogen species H2O, right. So, that is how, that is why I have written this expression, and from this it is you can obtain Q out as 285,830 kilojoule per kilomole. So, that is the amount of heat that is being released. So, this is kilomole of hydrogen, okay, right. So, we have solved the first part of this problem. So, determine the heat transfer from the combustion chamber, that we already obtained. Now, what will happen to our answer if combustion were achieved with 50% excess air? Now, if you supply more air here, okay, more air, 50% excess air, that means you are supplying more air, and then you are again taking out the entire heat from this, and all the products in addition to the excess air all are coming out at 25 degree centigrade. Okay. Now, what will be the heat transfer in that case? See, the heat transfer will not alter because both the reactants and the products are coming out at the same temperature again, okay, and the products will not absorb any energy because whatever product is coming out at 25 degree centigrade. Okay. So, therefore, our answer will be unchanged. So, the same amount of heat transfer will be obtained during the combustion process, even if we mix with 50% excess air. Okay. So, this brings us to the end of this problem. So, I will now go to the second problem. The second problem is about an adiabatic constant volume tank. So far we considered this as a constant pressure process, but now we are trying to solve a problem for a constant volume tank. So, let us say we have a tank. Here you have hydrogen and air mixture at 25 degree centigrade and 1 atmospheric pressure. Now, you are igniting this mixture and you are assuming complete combustion. We have to find the final temperature. Okay. So, final temperature, let us say Tf, and final pressure Pf. So, we have to determine them. Okay. So, this is an adiabatic constant volume tank. So, both Q dot and W dot is equal to 0 in this case. Okay. So, to start with, again we have to write down the balance equation. So, here hydrogen plus air, again it is a stoichiometric amount of air. Okay. So, I will write half O2 plus 3.76 N2, that is going to H2O plus 1.88 N2. Okay. Now, these reactants are at 25 degree centigrade, 1 atmospheric pressure, and we do not know what is the final temperature of this product, and we do not know what is the pressure of this product. We have to find this. Okay. So, to begin with, again we have to start with the first law of thermodynamics, which states that E in minus E out is equal to the delta E of the system, and we and it is basically 0, right. And what you have to do, you have to consider all the energy interactions, and we know that Q and W is both 0. So, I can write basically energy in the initial state should be equal to the energy in the final state, right. So, here for this constant volume case, we need to consider the internal energy as the parameter. So, what I will write, so this basically will give us to this form where I have to make a balance between the internal energies of the reactants and the product species. Okay. Okay. So, now we know that internal energy can be written as enthalpy minus PV, right. Now, this enthalpy I can write it as enthalpy of formation, okay, plus sensible enthalpy, which is again H minus H naught, and here we had internal energy, and you know internal energy is nothing but H minus PV, right. So, this is nothing but H, whatever we have written here, and then you have to subtract PV, and this PV is basically RUT, right. Okay. So, I can just substitute it as RUT, and so this is the reactant species, and that should be equal to the product species, which is NP HF naught plus H minus H naught minus RUT. Okay. This is for the product side. So, now we have to know what are the different enthalpies, and then only we will be able to solve this problem. So, again I will make a table for all the species. So, what are the species that we have? H2, O2, N2 and H2O in gaseous form, and now I will write out the enthalpy of formation in kilojoule per kilomole. So, this should be 0, 0 and 0, and for water the enthalpy of formation is 241,820 kilojoule per kg. Now, enthalpy at standard 298 Kelvin, that is the second column I am writing, and from the table at the end of the book of Sanger and Bowles or any other textbook on combustion or thermodynamics, you can find enthalpy of enthalpy for different species at different temperature. So, from that table you have to see that what is the enthalpy corresponding to this 298 Kelvin. Okay. So, if you look at for hydrogen, you will find it at as 8468. For oxygen it is 8682, for nitrogen it is 8669, and for water vapor at for water in the gaseous form, the enthalpy of enthalpy is basically 9904 kilojoule per kilomole. Okay. So, now we have to put these values into these expressions. Okay. So, let us first write down the reactant side. So, in the reactant side we have basically we have, if you see 1 mole of hydrogen, half a mole of oxygen and 1.88 mole of nitrogen. So, these are the reactants. So, if we evaluate the reactants, so that will give us 1 mole of hydrogen, and the enthalpy of formation of hydrogen is 0. Okay. Now, we have to find what is the enthalpy of formation of what is the sensible enthalpy, because here if you see. Okay. So, for this, let us rewrite this expression again. So, I will write this in the next slide. So, first I will write down the product species. So, NP, which is nothing but the products number of moles of the product species, HF naught plus enthalpy at any temperature T. Let us say Tp is the temperature of the product that is coming out. T we have written already Tf, right. So, Tf is the final temperature of the product minus enthalpy at 298 Kelvin and minus RUT of the product. Now, this T is nothing but Tf, that is the final temperature. So, this is the product side, and that should be equal to the reactant side. So, that is equal to NR, enthalpy of formation of species plus enthalpy at T equal to 298 Kelvin. Okay. because if you see the problem statement that the reactants are initially at 25 degree centigrade. So, what will happen to the sensible enthalpy? Sensible enthalpy will be 0, right. So, because H naught is enthalpy at 298 Kelvin and the reactants are also at 298 Kelvin. Okay. So, basically the difference will be 0. So, I am not writing that here. Okay. So, only the enthalpy of formation of the species will be there, and then you have Ru T reactants. Okay. So, that is the final form. Now, if you look at the table whatever you have already written in your copy. So, you please refer to these numbers and just use this number in the expression. So, to begin with, in the product side I have water. So, 1 mole of water. So, this is 1 multiplied by minus 241820, that is the enthalpy of formation of water. Sensible enthalpy of water we have to find, and let us say this is basically not known to us. Okay. What is the sensible enthalpy of water? So, let us say this is the enthalpy of water at Tf, and now you have enthalpy of water at 298 Kelvin, that I have written already in the table, that is 9904, and here Ru times Tf. So, Ru is the universal gas constant, which is 8.314 kilojoule per kilomole Kelvin multiplied by Tf. Now, Tf is unknown. Okay. So, that should be so that this is the H2O. Now, we have to see what will happen to the nitrogen. Okay. So, nitrogen is also present. So, there is 1.88 moles of nitrogen that is present in our system, and we have to now write enthalpy of nitrogen at the flame temperature, that is Tf, minus enthalpy of nitrogen at 298 Kelvin, which I have written as 8669 in the table. So, that is, and then I have to subtract Ru times Tf, that is 8.314 times Tf. Okay. So, that is for the nitrogen. On the right hand side we have the reactant species, and you have 1 mole of hydrogen, and the enthalpy of formation of hydrogen is 0, minus Ru is 8.314 and temperature of the reactant is 298 Kelvin. Okay. So, this is for hydrogen. Now, you have half a mole of oxygen. So, 0.5, and enthalpy of formation of oxygen is 0, minus Ru, that is 8.314 times 298, that is the Ru times T. Now, you also have nitrogen, that is 1.88 mole of nitrogen, for which the enthalpy of formation is 0, and it is 8.314 into 298. Now, if you do the algebra, you will find enthalpy of H2O at Tf plus 1.88 times enthalpy of nitrogen at Tf minus 23.94 times Tf, that should be equal to 259648 kilojoule. Okay. So, just the calculations. Now, this is the final form that you are getting. What you have to do? You have to find now Tf. Okay. So, there is I mean we can obtain this Tf by trial and error method. Okay. So, what I will do? I will first guess a temperature, let us say T guess. Okay. So, first I will guess Tf as 3000 Kelvin, okay, and then I will evaluate the left hand side. So, basically this side, this expression I will evaluate. Okay. So, if I assume Tf equal to 3000 Kelvin, I can find the enthalpy of H2O and nitrogen from the table, and I can calculate the left hand side. So, left hand side will come out as 255 0.089 kilojoule. Okay. Now, what is on the right hand side? We have 259,648 kilojoule. So, this is not matching. So, we have to make another guess. So, let us say Tf is 3050 Kelvin, and for that if you evaluate this left hand side, you will get it as 260,163 kilojoule. Okay. So, now you see that on the right hand side you have some value which is in between these two numbers, right. So, what I have to do, you have to interpolate, and by interpolation you can find what is the Tf. So, Tf after interpolation you will get it as 3045 Kelvin. So, that is the final temperature of the product gas inside this constant volume reactor. Now, you can find what is the pressure, that is the final pressure. So, for that what I have to do, I have to basically write down the equation of state. So, PV equal to N RU times T. What is N is the number of moles. Okay. So, now let us say initially the reactants were at Pi, volume V is constant. Now, Ni is the initial moles of number of moles of the reactants, Ru times Ti. Okay. These are the initial states, and the final state it is Pf V, Nf is the final total number of moles of the product gases, Ru times Tf. So, I got these two expressions. Now, if I take the ratio of this, I will get Pf over Pi as Nf over Ni times Tf over Ti. Okay. So, now I can find what are the values of Nf, Ni, and I know Tf is 3045 and Ti is 298 Kelvin. Okay. So, let us say from this balance equation I can find what is the Ni. Ni is the number of all the reactant species, which is 1 plus 0.5 plus 1.88. Okay. So, you will get it as 2.38. Okay. So, this is the number of moles of the reactants, and Nf is the number of mole of the product gases, which is 1 plus 1.88, that is 2.88. Okay. So, now I can substitute these numbers here. So, this is 2.88 divided by 2.38, and Tf was 3045 Kelvin, Ti is 298 Kelvin. So, from this you will get Pf is, and Pi is basically 1 atmospheric pressure, right, that is given in the question. So, you can evaluate Pf as 8.7065 atmospheric pressure. So, this is the final pressure of the system, and Tf is the final temperature of the system. Okay. So, in this problem we have seen a constant volume reactor, and we have calculated the final temperature and the pressure of this system. Okay. So, we started with the energy balance, and we have obtained that the total energy of the reactant should be equal to the total energy of the product. So, basically here for the constant volume system we have to consider internal energy and not enthalpy. Okay. So, internal energy you can write as H minus PV, and then this PV you can write it as RU times T, and then you can obtain this relationship. Okay. And after that you have to just plug in the numbers, and in this problem you have to obtain the flame temperature by doing some trial and error method. Okay. So, now I will move to the third problem. So, here the problem statement is that liquid octane enters a steady flow combustion chamber at 25 degree centigrade and 8 atmospheric pressure. Okay. So, there is a combustion chamber where liquid octane, that is C8H18, enters at 25 degree centigrade and 8 atmospheric pressure, and it is burnt in presence of air which enters at, which is compressed and preheated. Okay. So, it is at 8 atmospheric pressure and 500 Kelvin. So, this is the combustion chamber, and its pressure is 8 atmospheric pressure. So, it is a constant pressure chamber, where air enters at 8 atmospheric pressure and it is preheated to 500 Kelvin, and the liquid octane enters at 25 degrees centigrade at same pressure, 8 atmospheric pressure. And finally, the product leaves out this combustion chamber, and after combustion the product enters an adiabatic turbine. So, there is a turbine which is adiabatic, where it expands and leave at 950 Kelvin and 2 atmospheric pressure. So, that is the exit state of the turbine, and in this process there is some work done by the turbine. Okay. So, assuming complete combustion and T naught is the surrounding temperature, which is 298 Kelvin, 25 degrees centigrade or 298 Kelvin. So, first we have to determine the heat transfer rate from the combustion chamber. So, there is some heat transferred from the combustion chamber, we have to determine that, and the power output of the turbine. And the third question is that the reversible work. So, W dot reversible of the turbine and exergy destruction, okay, for the entire process. So, this is the question. So, we will again begin with the balance equation. So, we have C8H18, which is, let us say, that is reacting with air, which is O2 plus 3.76 times N2, and that is producing, that is complete combustion. So, it will lead to 8 CO2 plus 9 times H2O, and there will be some nitrogen. Now, what is said that it is 200% excess air. Okay. So, first we have to find out the stoichiometrically balanced equation, then we have to make 200% excess air. So, let us say I will first write it as the balance equation, which is the stoichiometric equation first. So, here if you want to balance both left hand and right hand side, you see that you have to make some mole of air basically. So, ATH is the theoretical air, and that should be equal to 8. So, here you can see that how many mole of oxygen is needed. So, 8 moles of oxygen, and here you need 4.5 moles of oxygen for water. Okay. So, ATH theoretical mole of air will be 12.5. Okay. So, now actual equation, actual balance equation. So, this is the stoichiometric equation. Now, if you write actual equation will be C8H18. Now, it is saying that 200% excess air, that means whatever air is needed for stoichiometric balance, you need to give 200% more air, that means it will be 3 times ATH, right. Okay. So, ATH is 12.5. So, 3 times ATH is 37.5. Okay. So, that much mole of air has to be provided, and this is the left hand side of the reaction, and it will be 8 times CO2 plus 9 times H2O. Okay. And then there will be some nitrogen. So, nitrogen will be 141 times nitrogen, and there will be some oxygen left, which will be 21 moles of oxygen. So, this equation is not balanced. So, here you can write how much nitrogen will be there. So, nitrogen will be 12.5 times 3.76. Okay. So, then it will be balanced. So, this is the actual reaction now. So, you can see the product species will have some CO2 and H2O, and there will be lot of nitrogen and some amount of oxygen, because you are supplying additional air for combustion. Okay. So, now we can do the energy balance across this reactor, and we can find what is the amount of heat that is that is transferred from the combustion chamber, right, that is Q out. Okay. So, I will again start with E in minus E out is equal to delta E of the system. Okay. So, here I will assume that there is no work done by the combustion chamber. So, we are only considering the combustion chamber at this moment. So, whatever energy is going out is because of Q out, and the products are also going out. So, that we have to consider. So, that should be equal to enthalpy of the products. Okay. So, Hf naught plus H minus H naught of the product. Okay. And then you have to subtract the enthalpy of the reactants. So, Hf naught plus sensible enthalpy of the reactants. Now, again I will have to make a table, and then we can easily calculate what is the amount of heat that is going out of the combustion chamber. So, in the next page I will just write out the table. So, you have the species, then I have the enthalpy of formation. So, I need a big table basically. So, I will start again. So, the species, then enthalpy of formation, the unit is kilojoule per kilomole. Then you have the enthalpy at 500 Kelvin, because if you see that the reactants are coming at 500 Kelvin, that is air. Okay. Then I will write enthalpy at 298 Kelvin, all the units are in kilojoule per kilomole. The enthalpies of the combustion product are leaving at 1300 Kelvin. So, I have to do this, and if you see that the combustion gases after expanding in the turbine, it leaves at 950 Kelvin. So, again I will make another column where I will write the enthalpy of the product enthalpy at 950 Kelvin. Okay. So, these are the values that I have to find from the table. So, we have to again look into the appendix of the book Cengel and Bowles. So, appendix 18 to 23 where you can find all these species. So, first species is C8H18, and that is in the liquid phase, and if you look at the table you will find it, the enthalpy of formation is 249950. So, we do not need this enthalpies. Okay. Next species is oxygen. So, air is coming in at 500 Kelvin. Enthalpy of formation of oxygen is 0, but enthalpy of enthalpy at 500 Kelvin for oxygen is 14,770. Enthalpy of oxygen at 298 Kelvin is 8682. Enthalpy of oxygen at 1300 Kelvin is 40,170, and enthalpy of oxygen at 950 Kelvin is, sorry, this will be 42,033, and then at enthalpy of oxygen at 950 Kelvin is 26,652. So, this is for oxygen. Next I can get the values for nitrogen, that is enthalpy of formation is 0. This is 14,581, this is 8669, 40,170, 28,051. H2O is in the vapor phase. So, enthalpy of formation is minus 241,820. Water vapor is basically the combustion product, and which is at 1300 Kelvin, right. Okay. So, water vapor exists at 1300 Kelvin and 950 Kelvin. So, we have to write the enthalpies at 298 Kelvin of water vapor is 9904, and at 1300 Kelvin it is 48,807, and this is 33,841. This is for the water vapor. Next is CO2. Enthalpy of formation is this much. CO2 also exists at high temperature, that is 950 and 1300 Kelvin. So, you do not need here. So, this is 9364, and this is 59,552, and this value is 40,070. So, these are the values of enthalpies of different species. Now, we have to just plug in the numbers here. We know we are now balancing the energy across the combustion chamber, and we know what are the reactant species. Reactant species are O2 and N2 and the octane, and the products are this CO2, H2O, N2 and O2. So, we have to write individual enthalpies of different species, and then finally, after substitution you will get minus Q out, that is equal to 8 times, this is the CO2 enthalpy, and this is coming out at 1300 Kelvin. So, sensible enthalpy will be difference of 59,552 and this one. So, this is the sensible enthalpy of CO2 and this is the enthalpy of formation. Now, you have 9 moles of water vapor, for which the enthalpy of formation is this one, and sensible enthalpy at 1300 Kelvin will be difference between these two. Now, you have I think this will be 25 moles of oxygen. So, you have 25 moles of oxygen, which is enthalpy of formation is 0, but the sensible enthalpy at 1300 Kelvin will be difference between these two numbers. So, 40170 minus 8669. Now, next is the nitrogen, which is 141 mole of nitrogen, enthalpy of formation is 0, and this will be, sorry, I think these numbers are actually misplaced. So, for oxygen it will be 42033 minus 8682, and for nitrogen it will be 40170 minus 8669. So, these are the enthalpies of the products. Now, what about the enthalpy of the reactants? We have to now consider that. So, 1 mole of octane is coming in. So, let us say 1 times enthalpy of formation is this much, and there is no sensible enthalpy because it is coming at 25 degree centigrade itself. Okay. Now, what about the other species? We have 37.5 moles of oxygen. So, this is 37.5 moles of oxygen. Enthalpy of formation of oxygen is 0, and sensible enthalpy of oxygen at 500 Kelvin is basically difference of this and this. Okay. Sorry, I am always taking wrong number. So, sensible enthalpy of oxygen at 500 Kelvin is difference between this and this. So, 14,770 minus 8682. So, that is the sensible enthalpy of oxygen. For nitrogen, there is 141 moles of nitrogen. So, enthalpy of formation of nitrogen is 0, and absolute sensible enthalpy will be difference between these two. Okay. So, now we have considered all the species, and from this if you calculate this is a big expression, you will find the value as this much kilojoule per kilomole of C8H18. Okay. So, that is the amount of heat transfer. So, Q out is 109,675 kilojoule per kilomole of octane. Now, if you look at the rate of supply of octane is 0.8 kg per minute. Okay. So, octane is entering at 0.8 kg per minute. So, m dot is 0.8 kg per minute. So, you can find what is the rate of supply of octane in kilomole per minute. So, n dot is kilomole per minute, that will be m dot divided by the molecular weight of the octane. So, this is 0.8 kg per minute divided by molecular weight of octane is basically C8H18. So, it is 8 into 12 96 plus 18. So, 96 plus 18 is 114. Okay. So, molecular weight of octane is 114. So, you will get it kg per minute. Okay. So, it will be not kg, it will be kilomole per minute now. Okay. So, this value is 7.018 into 10 raised to power minus 3 kilomole per minute. So, the total amount of heat transferred will be 109675, and I have to multiply it with 7.018 into 10 raised to power minus 3. So, this will be kilojoule per minute, okay, which is nothing but 770 kilojoule per minute. Okay. So, this is the answer for this problem. Next, we have to calculate the power output of the turbine. Okay. So, this is an adiabatic turbine. So, there is no heat transfer from the turbine. Okay. So, to do this, what I have to do, I have to again consider the energy equation across the turbine. So, for the turbine, if you see that you have the turbine, here the combustion gases are coming at 1300 Kelvin and 8 atmospheric pressure, and it is producing some W dot turbine, and it is leaving at 2 atmospheric pressure and 950 Kelvin. Okay. So, W dot out is basically the difference of enthalpies. So, let us say enthalpy of the product, okay, at the inlet. So, this is at the inlet enthalpy and this is at the exit. So, I can write it as enthalpy difference between the exit and the inlet. Okay. So, from this I can find W dot out as summation NP enthalpy. So, there is a minus sign. So, minus sign has to be taken care. So, it will be HI minus HE, or I can write it as summation of NP enthalpy of the product gases at 1300 Kelvin minus enthalpy of the product gases at 950 Kelvin. Okay. So, we have already written the enthalpies here, right. So, from this we have to now proceed, and if you calculate W dot out is basically the difference of the sensible enthalpies, right, between 1300 Kelvin and 950 Kelvin. So, first I will say that what are the species that is available you have in the product. In the product gases you have 8 moles of CO2, 9 moles of H2O, 25 moles of oxygen and 141 moles of nitrogen. Okay. So, we have to now calculate individually. So, let us first begin with CO2. So, 8 moles of CO2, and now enthalpy of CO2 at 1300 Kelvin from this table, it is this value, and enthalpy of CO2 at 950 Kelvin is this value. So, you have to take the difference between these two. So, 59,522 minus 40,070, and there are 9 moles of H2O, and the difference of enthalpies between 1300 and 950 Kelvin, again you can refer to this table. So, this is the difference between these two numbers you have to write. So, it is 48,807 minus 33,841. Then you have oxygen, which is 25 moles, and from the table you take the numbers, and for nitrogen it is 141 mole, and the difference of enthalpies is this much. So, from this you will get the W dot out as this much kilojoule per kilomole of C8H18. Okay, so that is the amount of work done by the turbine. Now I can write it in kilojoule per I mean kilowatt basically. So what I have to do, I have to multiply it with n dot basically. N dot is the value that we already obtained as 7.018 into 10 raised to power minus 3. Okay. So 2245164 into 7.018 into 10 raised to power minus 3, and this will come out as 15,756 kilojoule per minute. You can convert it into kilowatt and you will get it as 262.6 kilowatt. So that is the work output from the turbine. Now coming to the third part of the problem, the reversible work and the exergy destruction during the process. We have to now calculate the entropy. Okay. So exergy destruction is nothing but T naught times entropy generation during the process. Okay. Now S dot gen we have to evaluate, and S dot gen can be evaluated from this expression. You know that it is the entropy of the product minus entropy of the reactant, and then the amount of heat that is going out of the combustion chamber divided by the surrounding temperature. Now you have to first calculate SP and SR, and then you already know what is the Q out of the combustion chamber, which we already obtained, right. So first we have to get what are the values of this. So for that we have to now obtain the entropy of individual species. So entropy of the individual species can be obtained. So let us say entropy of a species at temperature T and pressure Pi can be written as entropy of that species at reference state and temperature T. Reference state is basically P equal to P naught at atmospheric pressure minus RU times log of Yi times Pm. Okay. So Pm is basically the partial pressure that we have to calculate. Okay. Now, so Pm is the pressure, right. So this is basically Yi is the mole fraction, so Yi times Pm is the partial pressure, right, is the partial pressure. So let us do this. We have different species like C8H18, and you have the number of moles of this species, number of mole fractions of this species, and you have the standard entropy at temperature T and 1 atmospheric pressure, and then this column is RU times log of Yi times Pm, and then this is Ni Si bar. Okay. So we have different species like octane, oxygen and nitrogen, and we know that 1 mole of octane is going in and oxygen is 37.5 mole. So these are the reactant species, and nitrogen is 141 moles. So mole fraction of octane in the stream is basically 1, and mole fraction of oxygen will be 0.21, that is basically ratio of these two, and mole fraction of nitrogen is 0.79. Okay. Now from the table you can find what is the entropy of this species at 1 atmospheric pressure and the temperature that is given. So for octane it is entering at 25 degree centigrade, and entropy from the table you will find it as 360.79 kilojoule per kg Kelvin. For oxygen it will be 220.589, and for nitrogen the value is 206.63. Now you can calculate this parameter. Okay. Ru is 8.314 kilojoule per kilomole Kelvin, and Yi is the mole fraction that is given here, and Pm is the pressure, the total pressure. Okay. So, let us say this is Pm is here 8 atmospheric pressure, right. So, you can basically put in the numbers here and calculate these numbers. Okay. So, Yi you have to take it from this column, and Pm is 8 atmospheric pressure and Ru is 8.314. So, this is 8.314 times log of 8, okay, and that you calculate it as 17.288. Similarly, here the value will be 8.314 times log of Yi is 0.21 and Pm is 8 atmospheric pressure. So, 0.21 times 8 and you have to take a log, the value will be 4.313 and here the value will be 15.329. Now, you can evaluate this parameter. So, this parameter NiSi bar is basically NiSi naught plus, not plus, so it is at some T and P naught minus Ru log of Yi times Pm. So, that is the expression that we are evaluating, and you have now already obtained this parameter and you already have the standard enthalpy, and now you have to multiply it with the mole fraction, and if you do that you will evaluate this column. So, this value will be 343.5, this will be 8110.34 and this will be 26,973.44. Okay. So, if you add all these species, then you will get SR, that is the entropy of the reactant species, and that will be 35,427.28 kilojoule per Kelvin. Okay. So, that is the you can calculate the total enthalpy of the products. Okay. For the entropy of the products, we will again write CO2, H2O, O2 and N2. These are the product species, and again I will write this column basically. That will help us in calculating entropy of the product. Okay. So, first I will see what is the number of moles of CO2 in the product gases, that is 8, number of moles of H2 is 9, number of moles of oxygen is 25 and number of moles of nitrogen is 141. So, if you calculate the mole fractions, it will be 0.0437, this is 0.0490 and this is 0.1366 and this is 0.7705. See, the number of the mole fraction is basically this number of mole of that species divided by number of mole of all the species. Okay. So, basically for CO2 it is 8. So, basically Y CO2 is 8 divided by 8 plus 9 plus 25 plus 141. So, that is 0.0437, right. So, that is the mole fraction. Now, from the table you can find what is the entropy of this species at the temperature that is given, right. So, T is equal to 950 Kelvin, right, where the gases are leaving the turbine. Okay. So, the temperature is 950 Kelvin where all these species are leaving the turbine. Okay. And accordingly you can find what is the entropy of CO2 at 950 Kelvin and 1 atmospheric pressure. So, that is 266.444 kilojoule per kilomole Kelvin. H2O it is 230.499, for oxygen it is 241.689, for nitrogen it is 226.389. So, this is the entropy, standard entropy. Now, because it is at high pressure, so you have to account for that, right. So, that is why we are basically subtracting this term Ru times log of partial pressure I mean of the species. So, what we are doing is here the pressure is 2 atmospheric pressure, right, where the gases are leaving the turbine. Okay. So, if you evaluate this parameter RU times log of y times P, this will be minus 20.26, this will be minus 19.281, and this will be minus 10.787, and this will be 3.595. Okay. So, RU times log of yi times Pm, and now if you calculate NISI bar, which is nothing but this expression what I have written here, that is how we are evaluating the last column. So, if you plug in the numbers and do the calculation, you will get it 2293.63, 2248.02, 6311.90, 31,413.93, and now you have to add all of them, and after adding you will get entropy of the products that is leaving the turbine, and this is the value in kilojoule per Kelvin. Okay. So, now you know this, and we can now calculate the exergy destroyed during this process. So, x dot destruction is basically T naught time S dot generation, which is T naught is 298 Kelvin, and S dot generation is nothing but SP minus SR plus Q out divided by the surrounding temperature. So, that is 298 Kelvin, 42,267.48, SR is 35,427.28, Q out is 109,675 kilojoule, and the surrounding temperature is 298 Kelvin. So, the answer will be okay. So, this will be this is the value. Now, we also have to multiply it with that n dot, right. Now, n dot is the molar rate of supply of octane. Okay. So, that value of n dot what we have written already is 7.018 into 10 raised to power minus 3 kilomole per minute. So, this unit if you find it, it will be 50.59 kilojoule per minute Kelvin. Okay. So, that is the exergy destroyed. So, this value will be if you evaluate this, it will be 15076 kilojoule per minute, and if you obtain in kilowatt, it will be 251.3 kilowatt. So, that is the exergy destroyed during this process. So, now if you want to obtain the amount of reversible work done, so what you have to do, you have to add the actual work done of the turbine and the exergy destroyed. So, that will give you the amount of the reversible work. So, let us do this. So, W dot reversible will be nothing but W dot turbine, which is the actual work output of the turbine, plus exergy destruction. So, W dot T we evaluated as 262.6 kilowatt and exergy destroyed is 251.3. So, this will be 513.9 kilowatt. So, that is the amount of reversible work done that is possible, but in the actual case we are seeing that we are only getting this much work done from the turbine. Okay. So, in this process, in this problem we have done a thorough study of different things. This includes the heat transfer from the combustion chamber, and then finally we obtained the amount of work done from the turbine, and finally we also calculated the exergy destruction during the entire process of combustion and the work done in the turbine and the amount of reversible work done. Okay. So, this brings us to the end of this tutorial, and I am closing formally this tutorial on thermodynamics. So, we have covered different aspects, different topics of the thermodynamics. So, in the first half of this tutorial series, my colleague Dr. Jishnu Bhattacharya offered 10 tutorials, and I also offered remaining 10 tutorials I started with the air standard cycles and then vapor power cycle, refrigeration, thermodynamic relations, and today the chemical reactions. So, thank you for your attention and all the best.